Very good. Awesome. Normally I like to walk around when I present, but my cable is short, so I will be standing right around here. So welcome to the afternoon of NIWeek, second session of the afternoon of NIWeek. So if you're not aware, today we're going to be talking about transitioning to the LabVIEW Brito architecture. Before I get started, I wanted to get input from a couple people in the room as to kind of what they're working on and what they're looking to get out of from today, just to see, kind of make sure that I kind of get everyone's questions answered. So, audience participation. I'm going to wait until someone applies. Yes.
So, the talk is called embedded, embedded. So you're not going to be covered like ARM processors or something like that.
What I'm going to be talking about is how you program for those embedded targets with LabVIEW. So yeah, the title is slightly different, but it's the same, one and the same. So yeah, we're going to be talking about LabVIEW on embedded targets. Anybody else have anything specific that they're looking to get out of today? Anything? Well, we'll get started. So my name is Rahul. I'm a LabVIEW product manager here at National Instruments. Also a certified LabVIEW architect. So if you have any questions about your application after the session, I'm more than happy to sit down and chat. Today we're going to be talking about transitioning from programming in current LabVIEW to programming for an embedded target. And so why are we really here today? So, all of you have come from, all over the US and all over the world to really program whatever applications, whether it's in oil and gas or medical devices or aerospace or whatever it may be. And so, really with the applications that you all are working on, you all have more and more demands for reliability and for performance. And so that's really where this idea of embedded devices comes in, and this idea of the LabVIEW Brito architecture. So for those of you who were at the keynote this morning, we saw this icon a lot, the LabVIEW Brito architecture. And so what it really is it's a processor with an FPGA and then all your inputs and outputs. So for those of you who have worked in the embedded space before, obviously this idea of having a processor with an FPGA is not necessarily a new concept. So what really brings this all together is the fact that you can program on both of these targets using LabVIEW. So instead of having an expertise in C and someone else having an expertise in hardware definition language, you can basically translate the current skills you have in LabVIEW to programming in this architecture with the 10 things we're going to talk about today. And what's really cool about this architecture is that you can use it for a wide range of hardware targets. So all of you will have different applications you're working on or considering working on, and each will have different sort of hardware requirements. So if you're looking at something more custom or more deployable, you'll probably either look at the SBRIO or the SOM. So the SBRIO is basically the processor and the FPGA with a bunch of built-in peripherals and the ability to interface with our I/O that we already have in-house. The SOM is basically like the LabVIEW re-architecture on a chip, and at that point, that's usually for like very high deployment OEM type of applications where you would then have the expertise of building the hardware board around it. So the SOM is a little bit different in terms of the upfront work that you have to do on the hardware definition side. Then sort of the mothership that you hear about a lot is the compact Brito. So this is going to be the single board Brito that we talked about previously, but in a kind of hard, ruggedized chassis. So again, high vibration, low or high temperature type of applications. You can throw it out in the field and they'll run for months or years. You can interface with all our C-series modules, so analog inputs, outputs, temperature, motion, CAN, what have you. What I have here today, for those of you who like to actually touch and look and feel, is a compact Brito in a compact Brito demo kit. So this is up for your viewing pleasure after the talk. And then finally, the LabVIEW Brito architecture also translates to those sort of high-performance types of applications. So what that usually means is very high data rates, or so if you're talking about like gigabits of data, or if you're talking about RF or something like that. That's where you're going to typically talk about high performance. So in that case, you'll either use a Flex Brito or an R-series card. So those will be sort of the big DXi chassis that you'll see a lot there at NIWeek. Or at the keynote today, they announced the new compact Brito, or the controller for Flex Brito. So that's a deployable Flex Brito for high performance application. And so, again, what we learned today will allow you to start to look at these different hardware targets and see how you can program them for your specific application. So how many people have actually worked in LabVIEW before? How many LabVIEW programmers do I have? Okay, cool. That's what I was thinking. So how many of you are familiar with this type of either DAC workflow or file input and output? Kind of seeing a lot of nodding heads. Cool. So, so this is what we're used to. So if if you had a task in DAC, you'll open a connection to your channel, configure your sample clock, configure your triggering, and then you'll do something, in this case read your data in a loop, and then you'll close it and handle errors. This exact same thing looks like this on an FPGA. So very different. We'll really break out into some of the pieces of what this all means down the line, but this is sort of the paradigm at which we are approaching the session today. And so really it's going to be the top 10 considerations. These are sort of the top 10 big things that are different when you're programming for the LabVIEW architecture as compared to what you would normally used to be programming in lab. Who here, when they program in LabVIEW, uses the project? Who starts all their applications from the project? Cool. That is a good 70 or 80% of the room. Always, 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 always start from the LabVIEW project. It is basically, think of it as a very, very fancy XML file that keeps track of where all your files are in your project. It can do other things like build executables. For programming for an embedded target, the project is imperative. So most of you have probably seen this My Computer in the project before. And you might have wondered, well, obviously I'm programming on my computer. Why is that there? And the reason is because of this idea of different, basically, computers that you could program on. So there's my computer, and in this case we have our compact Rio target. So again, the compact Rio is its own embedded computer running its own operating system. So it shows up at the same level as my computer in the project. And then underneath that you see the FPGA target in the compact Rio. So again, to show a little bit of a demonstration, let's switch to LabVIEW. I got my I have a LabVIEW 2015 here. And so again, this kind of looks like what we see here. So this is a key kind of stumbling block that I see when a lot of people are starting programming for a Rio application. Is so this VI right here will run literally on my computer or on my computer's processor. If I were to take this VI and drag it under this compact Rio, now it'll run on my compact Rio, on the actual processor here. And so one sort of slip-up that people have is, oh, I'm trying to save something to a file, but I can't see it in my C drive. Well, a lot of a Linux operating system also has a C drive, and so it's probably saved on your Linux, on your Rio instead of your host processor. So again, it's very much an idea of different computers running the code on that specific target. Somewhat similarly, if I were to take this and drag it onto the FPGA, this would run on the FPGA, but again, there's more considerations that you have to take into account. So that's sort of, at a simple level, the idea behind this, sort of always working from the project. When you actually start to work into this, there's a couple of steps. It's like 3 steps to actually add your target that I'm not going to walk through today. But again, this should be the starting point for all your applications. So point 1B is you can program the mode of your embedded target from the project. So for the compact Rio and a lot of our embedded targets, there's something called scan interface mode. So for a lot of your applications, you will just need to program on the real-time side of things. We'll talk about what real-time means in a second. And you won't necessarily need the customization that you get on an FPGA. So that's what's called scan interface mode. So it deploys a fixed personality to your FPGA, and you get basically updates, single-point updates at a kilohertz or less. If you're trying to go to something faster, then you would have to go to FPGA mode. So we can see here, my wire will allow me. You basically just choose, and it'll be a dialog box instead of a blurry picture. And you can also configure this on a module-by-module basis. So as you get to more kind of complex applications, you might want some in scan interface, some in FPGA. But basically, point 1, use the project. Do not use the project, otherwise I will be very unhappy. All right, so now we're going to focus on the processor side of things. So again, there's 2 main keys here. There's the processor, and there's the FPGA that interfaces with your real-world I/O. And so, what are the considerations when programming for LabVIEW real-time? Who can tell me what do I mean when I say real-time? Yes.
Deterministic time.
Deterministic time, exactly. So when we're talking about real-time or a real-time operating system, we're talking about determinism. So that means if I want my control loop to run at this rate every single time, if I want to check the temperature of my very important material at the same time every time, that's what you get on a real-time operating system. If you contrast that to a Windows operating system, Windows is an operating system of fairness, basically. So right now I'm running PowerPoint, I'm running LabVIEW, I'm running Chrome, whatever else, Spotify, I guess. And so what my operating system is doing in the background is switching between all of those at a very fast rate to give me the idea that it's happening in parallel. What that means is that the operating system, Windows, gets to choose what is considered high priority, not you, the programmer. So if I'm running a very, very time-critical control loop, and Windows is like, oh, too bad, I'm going to run an update, or the proverbial antivirus scan, then that's Windows' purview, not yours. On a real-time operating system, we'll talk about how you do this, but the programmer gets to choose what is the top priority task or tasks, and all that type of thing. So that's really the important thing. A key thing to remember is real-time does not mean faster necessarily. It just means it means reliable and deterministic. All right, so point one was working with the project. We understand what a real-time operating system is now. So what are the different considerations that we have to take when programming on a real-time operating system? And the first is the reality of programming on an embedded device is that typically you have fewer resources. It just totally depends on your application. You might want an 8-core processor on your embedded target. That totally depends. But you typically will be dealing with limits in disk space, in RAM, and in your processor. And so those will typically look like, I only have, so many, like 512 megabytes of hard drive space, so I'm actually losing data. So there's workarounds for that. I only have so much RAM, not like the 16 that I'm used to on my PC, so I might run out of memory, or you might starve your processor. So these are all considerations. We'll talk about what compilation failures mean in an FPGA later, but again, embedded targets have constrained resources. That's point 2. So what do you do about that? There's a couple ways you can actually monitor the resource usage on your real target. So one is this thing called Distributed System Manager. So what this is basically a separate little program that you can run. It'll show you all your targets on your network, such as like your compact Rio, and it'll allow you to monitor CPU and memory. If you want to do this programmatically in your application, then there's what's called the System Configuration API, which allows you to, using these sort of property nodes and stuff that you're all familiar with, look at how much memory do I have available, what is my processor utilization, and then you can then do something about that. So point 1, always use the project. Point 2 is you're working with constrained resources. Point 3. So we talked about real-time operating system. We talked about how you, the programmer, are now empowered to choose what is a high-priority task, what is a low-priority task. And so what that looks like in LabVIEW is, instead of using your normal old log loops that you all have used in the past, wrong direction, you now use a time loop. Asterisks, don't use time loops on Windows. It does weird things. But on a real-time operating system, the stuff that you put in a time loop is going to be what is going to be your top priority task or your high priority task. It has this thing called, we call it an input node, and that allows you to specify the rate at which it's going to run. It allows you to specify what is the priority, so it's just like a number that you feed into it. And then this left data node will give you information on, did the loop finish late, how long did the loop take, so you can actually have that information accessible, and you can then make the corresponding decisions. And really what we're talking about when we talk about determinism is jitter. Who can define jitter for me? Who didn't read this slide? Jitter. Sorry?
Variation.
Yep, exactly. Variation in timing. So if I want my loop to run at every, at 2.03 microseconds, every loop's going to run within some tolerance of that. And the reality is, on a real-time operating system, this tolerance is going to be a lot less than on a Windows operating system. So that's sort of where this whole idea of determinism comes from. And so, this is our overall jitter profile, I guess. And so for your application, you're probably going to have some, tolerance to jitter. So in this case, we're saying, the bound is maybe that's 3 or whatever. So depending on your application, you're going to have some level of tolerance to what is determinism for you. The other key point I'll say about implementing high priority tasks, I guess point 3C, is not everything is by nature deterministic. So file I/O is not deterministic because you're waiting on your hard drive to respond back with whatever data you want. Network communication is definitely not deterministic because your computer doesn't have control over when things come back on the network. So just because something is put in a time loop doesn't mean it's magically going to be deterministic. So that's another kind of design consideration you have to make for things like file I/O, memory allocation. If you're calling a DLL, some DLLs are not deterministic by default. Those will have to stay in a normal loop. Whereas things like your PID control, motion control, any type of shutdown logic, all that type of stuff, we go in a time loop, and then there's tools to communicate between those two loops. So again, something you have to break out, another sort of caveat of this. So, point 1, use the project. Point 2, limited resources. Point 3, timed loops versus while loops. All right. Who has ever heard of a watchdog timer? Yes.
I'm sure, yeah. So if you were running PID control on real-time processor for mechanism,
Yes.
but also you can run on Windows LabVIEW and use the option in the PID where it actually measures the time of each loop and uses that to do the integration. Is there a trade-off there that you want to mention?
The trade-off, and it's a bit unfortunate. I was going to actually show kind of a demo that went across this point across, but my Ethernet port of my laptop broke.
Also, what's wrong with using time loops on Windows?
Sure. Yeah. So the two questions were: what are the trade-offs of using of running a PID loop on Windows, basically, when you can take the loop grade into account in your integration? And the second question was: what happens if you use a time loop on Windows? So for the first question, it really gets so. I think what we say as a rule of thumb is like, if you're fine with like 500 hertz or something like that, something that is okay and reliable to run on Windows. Otherwise, it just depends on how important it is for your application, because there's no way to really guarantee, the sort of plus or minus is going to be in the order of tens of milliseconds sometimes. And so it totally just depends on the application. How mission critical it is. The second question in terms of how time loops behave on Windows, I don't really have like a good answer to that because I've never really done it much, but all I know is that it won't behave as you want it to. Just because you say something is high priority or should happen first doesn't mean it will necessarily happen. So it's just weird, and I don't know if there's a good answer to that, but just I guess we don't do it. Any other questions? All right. Who can define for me, and somebody who has already answered questions, thank you so far, maybe someone from the back. What is a watchdog timer? Anyone heard of it? Who's heard of a watchdog timer before? If you raise your hand, what is a watchdog timer?
Basically, a watchdog is an independent loop that's running to pick the processor if it goes crazy.
Yep. That's a good way to do it. And basically, it allows you to make sure that your algorithm is crash safe, basically. So this is what code would look like. So watchdog timer is a hardware timer, and it is counting up, and then in your code you're going to whack or pet the watchdog, depending on how humane you are. The function's called whack. And so, if your software is running as it should be, it'll whack it every, whatever. But if, for example, your processor gets railed or you run out of memory, you won't whack it, and then your system will reboot when it counts up to a certain number. So this is really useful because we talked about limited resources earlier. It is really important to test your system for not just hours or even months sometimes, because when things are running as long as they are, performance is just going to happen, in weird ways depending on what the application is. So having this sort of watchdog timer will make sure that your code doesn't hang and then all your outputs are in a not safe state, when instead you'd rather just reboot, clear out the RAM, or free the processor and start over again. All right. Point 4, there's a watchdog timer at your disposal. All right. Point 5 is we are dealing with a deployed embedded target. This, my CRIO here doesn't actually have a desktop. There's a sort of a caveat to that I'll mention. But typically, what your system will look like is you'll have your device. It'll be on the network, either through your routers or switches, or directly connected to your laptop. And then you'll have your development computer. And so you're basically, when you're running code on the embedded device, it's going to be running the code on a processor, and in development, it'll just show that front panel on your computer. But really, at the end of the day, you're not going to have any kind of front panel on your CRIO or your SPRIO or your PXI system running real time. So typically, what you do is you'll have your embedded device. It'll run a real-time application, so you can have it at startup run like a headless application, and it'll just kind of run for as long as you want it to. And then you'll have a separate net application or VI running on your other PC that is communicating to that target over the network. So this will typically look like in final implementation is you can have, so this is the caveat. Some of our newer controllers have an embedded UI, which basically is like a touch screen, so it does kind of have like a little desktop thing, so like a lot of all the 90/30 targets that we just came out with in the last year. But generally, it's going to look something like this, where you have your network connection, and you'll either have like your touch panel computer, or just your regular laptop on the network, or if you another way that we really recommend to customers is you build a web service that is hosted on your embedded device, and then you either use your mobile phone, or you can use a product that NI makes called Data Dashboard, which is just a free download, and you can view your data, create kind of a fancy UI, or you actually develop your own web-thin client using HTML. So these are sort of the different ways that you can monitor your embedded device. All right, what brave soul can list for me the 5 caveats that we talked about so far? I don't know. I wish I had candy. Yes.
So using the LabVIEW project, real time for having reliability, using time groups for high priority tasks, parsing what's done, and the different model you have to make from.
Yeah, exactly. And the one subtle one you missed was the limits of resources. Yeah. So the 5 things we talked about so far. Always, 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 always use the project. It should just be start from project, not start from PI. And then second was you're working with limited resources. So depending on your hardware target, depending on the needs of your application, you'll have a certain number of resources. So it's always good to test that and to monitor that depending on your application. Third was for implementing high priority tasks. You have that control as a programmer. So use time loops. And the caveat with that is, like, we have embedded targets that go anywhere from 1 core to 4 cores to maybe 8 cores on the game size side. And so typically you're only going to want to have 1 control loop per core, or you're going to want to be careful about how you set the priority, so that you don't have like 4 things that are top priority but only 2 cores to run it on, because then you might not get things running as you expect. So you want to be aware of what is really high priority. The fourth was there's a watchdog timer, so a hardware timer that if your application hangs or crashes, you can have it then reboot. And then the fifth, was how you debug and deploy over the network. All right, so we've talked about the processor side of LabVIEW architecture. Now let's talk about the FPGA and the I/O. So again, the I/O goes through the FPGA to get to your processor, which is kind of why we have this sort of difference in paradigm of programming on real-time OS. Who can define for me what an FPGA is, to the best of their knowledge? Sorry? Yeah, logic gate array, exactly. And really, it stands for field programmable gate array. And how I like to think about it is, say you have islands of different processing units and DSPs and lookup tables, all floating in an unconfigured sea of interconnects. And then you, the programmer, define how those are connected. And there's, like hundreds of thousands in a chip. So you basically can implement almost anything you want in an FPGA. And the awesome thing about an FPGA is it's not running an operating system. So you're configuring the hardware. So this is really like true determinism. So with a real-time operating system, you'll say like microseconds. With an FPGA, you'll say nanoseconds. And another way to think about it is, because this is all in the hardware fabric, you can almost think of it as like an N-core processor, basically, because things run in true parallelism on an FPGA. Because this is a separate circuit from that. So there's no thread swapping. There's no operating system. It is defined hardware. So very powerful stuff. So point 6 on our road to 10 considerations when programming for the real architecture is how you actually interface with I/O in an FPGA. And so earlier in the presentation I showed, this is I think it was a triggered analog input in DAC versus an FPGA, and there are all those pink things. So this is one of those pink things. This is an I/O node, and this is saying module 1 analog input 0 is going to be the channel that I'm reading off of, or I'm writing to module 3 digital output 0 through 6. And so what you do here is every time you call this code, you're reading a single point of data from that channel. And so the limiting factor is going to be your module. So like an analog input module is going to have a certain spec on the ADC, and run at a certain rate. So say your module can do, 100 kilohertz. And you try and call an analog input read at 500 kilohertz. Well, what you're going to do is you're going to see repeat data because it hasn't actually updated. You're going to see the same set of data 5 times, which maybe you want to oversee. I don't know. Again, to kind of give a little bit more what this looks like. So if we go to our FPGA API, open over here. So over here. So this is kind of what I was talking about. So here, I'll talk about what this part means. I'll talk about the sequence structure in a bit, because you're probably like, flat sequence structures. I was told not to use those. I'll tell you a little bit more about why. But so this is what this is going to do is this is going to read from module 1, analog input 0, and analog input 1, and then it's going to add 2 to that one, and then build those into an array or into a big cluster. So yeah, it's again, you're literally reading straight from the hardware on your FPGA. So you can think about it as there's a lot of other signal conditioning and stuff, but your analog input goes to the ADC and then goes through stuff straight into the FPGA fabric. And so these support all the different types of data that you would expect it to. So whether it's a digital port, so 1 Boolean true or false, digital line, so again you're going to send like an 8-bit integer basically. Whether you're going to do analog inputs or outputs, so you can talk about integers or fixed point data. We also have C-series modules for motion and for CAN, and it can measure resistance and all the things that you're used to with the C-series module, strain, whatever. It's all the I/O nodes. That's what they look like. All right, point 6. You interface with I/O using I/O nodes. So the name is at least very, very apt. All right, who has ever heard of the idea of fixed point math versus floating point math? Okay, couple people. I think I'm done with quizzes at least for now. Don't take me at my word. But typically when you're programming for an FPGA or an ASIC, you're going to want to use fixed point math instead of floating point math because fixed point math is basically you have a defined range, you define where your decimal point is, versus floating point math, there's no defined decimal, so it has a very high dynamic range. Fixed point is typically going to take up less resources, and so it's going to be cheaper and more processing efficient than floating point. And so you can kind of see that here in terms of kind of how the fixed point number is defined versus the floating point number. And so these are kind of use cases for still using floating point on an FPGA. So you can still use floating point when you're prototyping or even when you're compiling. Just know that it'll use a lot more resources. So it really just depends on your application and your care abouts. So in this case, you use floating point math. You have your algorithm, which is in fixed point. In this case, that's sort of the grayish purplish wire. And then you want to convert it to float, so you can send it straight to your processor, and it can do whatever it wants to off the bat. The other is, it is quicker to just code in floating point, because in fixed point you're saying, my number has basically this range and resolution, and if you don't know that when you're first starting, you're probably going to do it in float, and then convert as the application requires. The other is if you do need very small numbers and very large numbers represented by one number, then that might suggest to use float instead of fixed. But again, caveat or consideration number 7 is this idea of using floating versus fixed in your algorithms.
What is the view?
Good point. So in 2015, so that they've come up with sort of optimized PID algorithms where you can actually program them in float, and I think they're just higher throughput and optimized to run on the FPGA more. So, proportional integral derivative. So it's basically it's an algorithm for running a control loop where you look at the previous number and the current number, and then you either compare it by multiplying by the p factor, integrating by the I factor, or
in general, I think I'm not restricted to fixed point.
Exactly. Yep. So the answer to the gentleman's question was, you're not restricted as much anymore to using float instead of fixed when programming on an FPGA. Just be aware that we've made work to optimize that, but it does take more resources on your money back. Yes.
Just for me to know, if I were to probe before this precision flow, and after the flow, get the same number, or I see something else?
I,
You see the blue line? If you
Yeah.
go to probe,
yeah.
what do you see?
The question was if you probe before the two precision float and probe after, would you see the same number? You would. I think it just depends on, because in this case, the fixed point is going to be more specific than the float. I think you might see it might just show it in like a different number of decimal places depending on how you find it. I've never actually tested that though. That would be
I was just
nice.
wondering if
Yeah.
I would probe.
Yeah, it should. I would demo that, but like I said, I can't do that. That's my doctor. Yes.
So how much time does it take if you're running PID?
Sorry.
How long does PID take if you're running fully
So the question was how long would PID take if you're running in float on the FPGA? I don't necessarily know if it's going to be a noticeable latency thing. I'm not sure, but I don't know if I have a good answer to that question. Because I think it would also depend on the rate you're looking for and the other components of your algorithm. I don't know. Does anyone else have experience with that? Looking at PID and float versus fixed on the FPGA?
Well, since you've got to integrate and differentiate, you have to do finite differences. And so you're going to at least have 2 clock cycles, probably more clock cycles for the implementation to do the finite differences. And so it'll probably be more than that.
So we
So my
take a
guess
couple
would
more.
be maybe 10 clock cycles.
Yeah, we expect to take a couple of clock ticks. And we'll talk about clock ticks in a second. Yeah. Yes. Yeah.
I'm sorry, I'm ignorant.
No, it's fine. Yeah.
That mathematical, whatever, can I add those 2 lines with simple icons? I have to have that conversion done before the process. I don't know if I'm clear. I mean,
No, yeah, so you're
can I
saying-
build an array with that?
I don't believe so, but we can actually check. Right. Go back to this guy. So we have here the program being over-enabled. So this is our. So the question was, can you just add your fixed point to your float point? And I don't remember if LabVIEW tries to coerce it, or if it gives you a broken arrow. So let us quick drop. You guys on the quick drop? Yes. Yeah, cool. Let's do a double constant. Constant. So this is, let's convert this to a double. Where it is. There we go. Cool. And so if we were to add these 2 guys together, it will. Okay, so it'll coerce to the higher fitted representation. So whether you can actually build these 2 into an array, build array. Array 2 here. And same thing. But it'll be an array of numbers. Not an array of things. So arrays do have to be the same data type and bitness, but it'll force it.
So, the divider is not kosher.
The divide, no. Because I don't believe, yeah, I don't know if it actually. I can't remember if it's not kosher in a single cycle time loop or if it's just not kosher at all. Well, because I mean, typically what you'll do is you'll send it to a multiply by a power of 2, and you'll give it a certain exponent. Yeah. We have this clean about the divide. Complaining now that I'm not sure. There's some caveats I'm forgetting about the divide, but I'll follow up in a second. The question was whether, because the divide is usually not allowed in the FPGA, got to figure out the caveats. Any other questions while I'm still here? Very good question. If I understand correctly, your question is how do you actually get your I/O into LabVIEW? So if we actually go back to the project. So when you add your if you were to add your compact Rio, then you can have it automatically detect your FPGA, and it'll also automatically detect the modules that you have in there. So in this case, we have our module, and then it also has module folder 1. And all I have to do is, so these are all the potential I/O on that module. And if I wanted to, I could rename this to something more logical to me, like cool sensor, if that was logical to me. And then if I just drag this in here, then that's my I/O. And if I wanted to read more than one data from my module, then that's kind of what we're doing here. So this will all be kind of read at the same time. Versus if I had, there's no timing association between these two. So what is in terms of like with the different aliases, or in terms of so LabVIEW will keep track of what that is for you in the background, and then that'll be stored in the bit file. So yeah, so if you change the alias and you know all that in your project, then LabVIEW keeps track of that for you. That's right.
So does error handling not exist on FPGA? That's why you use frames?
So no, that's actually not why. You actually can. There are still error terminals that you can use. The frames are for loop timing. We'll talk about actually in the next talk. What other questions? Well, if you have more, again, I'm more than happy. All right. So far on the FPGA, we've talked about, I believe, two considerations. We've talked about how you actually interface with I/O, with the I/O nodes, and we talked about this idea of float interface. What is next? So we talked a little bit about this already. We kind of alluded to this idea of clocking and timing. So you can either use a while loop, and there's a lot of details, but basically what you use the while loop for with the frames is you say run at this rate, so it'll basically count the timer, and then it'll run your code, and then count the timer and run your code. So it's kind of a weird looking implementation. Or you can use a time loop. So the question you probably have is, why would I use a time loop versus a regular while loop? And this is why. So if you have your code running in a regular while loop, the sort of enable chain that's happening in the background will operate such that it'll read the values from your controls, store them in some sort of memory register, and then at the next clock tick, it'll send that through the add, store that in another register, and so on and so forth. And so, that can be okay depending on your application, but if you want to, if you put something in a single cycle time loop, all of that will run in one clock tick. So it'll basically get rid of the intermediate registers in the background and just go from the start to the finish. And so you would see, depending on your application, some definite performance improvements using a single cycle time loop versus a while loop. That being said, there are functions that can't go in a single cycle time loop. So some functions by nature take more than one iteration to actually run, so they can't be put in one tick. For example, doing analog input and outputs by default takes more than one clock cycle. But you could read like a digital input in a time loop, for example. All right, point 9 is how do you actually transfer data from your FPGA to your processor? Obviously, your data comes in, you do something with it on the FPGA, whatever custom processing or high, low latency, whatever. So now we actually want that to our processor, and then maybe to our network, whatever it may be. And so there's a couple different ways that you go about doing that. So imagine at the top we have our FPGA VI, and at the bottom we have our real-time VI. And so say all I care about is single point. So I'm reading data, but I only care about periodically checking what that data is, or I want to send a stop, or I want to read the state of something. So just single point. So you use these things called read-write nodes. So first is on my FPGA VI, I put down a control on the front panel, and then basically the Rio driver registers that as it sees it as the control on the front panel. And then when you reference that specific FPGA bit file or VI in your real-time application, it'll have the list of those controls and indicators stored. So in this case, when I put in what's called a read-write control, it'll then see it and then allow me to, in this case, read from it. So if my FPGA VI is true there, then I'll read, this is a control. So if I want to start this, then I'll send a true for my RT, and it'll get sent down to the FPGA.
You have the open option actually to the FPGA.
Yes, so that's the part that I actually don't show here. So the first thing you would call, and I can show that in just a sec, the first thing you would have here is an open FPGA reference to actually open a connection to either by bit file or by the FPGA VI, basically. So the other examples here, so if I get a timeout here, then I can read that on my host, or if I'm just reading RPM data and I only care about reading that periodically, I can read that on my host. Question?
I've played with the FPGA a little bit. There's some things that were confusing. The one thing that you just mentioned was referencing whether from VI or from the bit file. What's the difference in that? What physically in the hardware or the software, what's the difference between referencing one over the other?
So, and so the question was, what's the difference between referencing the VI versus the bit file in your project? So, one example is, so usually, one use case for referencing the bit file is I've already done my compile, and then I'm basically just flashing the bit file, so I don't actually have to go through the compilation process. So if I have my real-time VI and I want to talk to the I/O using the FPGA, I can just deploy that every time, and I can just read straight from it. If you actually reference the VI, then
Is there situations where you want to do one over the other, or
yeah.
is there a best practice situation with those? How you reference it?
So I mean, so ultimately, usually you'll just end up referencing the bit file specifically. But I can't remember all the caveats. I'll follow up with you after the session because that is a good question. I just can't remember all the specifics.
I've seen the VI can be handy in situations where you're trying out a bunch of different FPGA designs, and it allows you to choose between them. But the bit file is usually for your final deployed application.
Yeah, I ran across a project one time that I didn't do it originally, but I stepped into it and the FPGA and all together, and I wasn't very familiar with it. It was a crash course in LabVIEW FPGA for me, and there were some things like that were unclear with how they did it. And in some cases, there were places where they referenced the bit file in the same code they referenced the VI, and I'm like, why? You know, what was the purpose behind that? And I don't know if they understood it either. So.
Question?
Is there a good rule of thumb for how many controls indicators you should put on the front panel of an FPGA? I know you shouldn't have too many, but
Yeah.
is there some limiting factor?
Usually you want to limit it, yes. You guys have hard questions today. I do believe it depends on the FPGA. I'm not sure if anyone has a thought on that. But I can follow up with you afterwards.
So I would say the short answer is that it just takes up FPGA resources the more controls that you have on the front panel. So if you don't need to access them from your host, then you don't want to have an indicator for it.
But I'm just wondering, what performance hit, what resource hits you take by putting more controls or indicators?
Right, yeah, and I'm not sure, like one control eats up this many slices, that kind of thing. It's kind of just a general rule of thumb.
Yeah, I mean, and obviously that's like one area that if you had a ton of controls and you're running out of resources, then like maybe you don't need all of those or something like that. But yeah, it's sort of only as much of a problem as is the resources available to you. Any other questions? Yes.
So in the FPGA, you're acquiring data at a rate, say 10 kilohertz, whatever it be. Can you read in the processor at the same rate? Is there the same like in the processor to do math, right? And you want at the same rate, we can see the same value.
No. So typically, so the question was if you're firing at a certain rate, and you're trying to read with like a read-write control, are you going to see the same value necessarily? And the answer to that is typically no. So usually your RTVI is going to be running slower than your FPGA VI. That's why this is just for like the single point case. If you don't care about every data point, you just care about the current data point. If you wanted to buffer it, then that's when you would use. That's when you could actually use some kind of FIFO or DMA FIFO. So if you actually cared about the stream of data, so this is a DMA FIFO architecture where it basically streams directly from the memory on your FPGA to the memory on your host, so it doesn't actually have to go through the processor. So that's going to be, so this is the same FPGA VI we saw in the last slide, and this is the part that's going to actually be writing to your FIFO. And so what that kind of looks like in the background is this cute little demonstration. Say I'm collecting tachometer and accelerometer data, at a certain rate. That's going to go through the FIFO, and there's a buffer on either side, and it's going to be then using the DMA controller be sent to the host. What this doesn't show is that if you were reading off this at a different rate than this. So say I'm streaming data really, really fast, and I'm reading it slower on my host side. You want to make sure, given your application, to optimize how large your buffers are, because you can configure the sizes of them, and the trade-off is using more memory on either side. But this allows you to read at a certain rate and read on the other end at a certain rate and not lose any data. But yeah, otherwise no, you probably lose data. Question?
But what about passing data between modules with peer-to-peer systems?
So do you mean like between FPGAs, or do you mean between like loops? So it depends on your hardware architecture. So if you have in a configurator that's just the one FPGA, so to actually transfer between an FPGA, your options would either be to send it to the host and then send it over the network. The other option would be to actually connect two different modules together externally, so it's like digital and analog. So that's just going to depend on the rates of the modules. With a lot of if you're using embedded targets on a FlexBrio, on a PXI system, then at that point, that's much more the use case for peer-to-peer streaming. So if you had two different FPGA cards, at that point, the limiting factor is the bandwidth plus. And so I think we have, by 3, or I think you can share with like 24 gigabits a second through.
Do you use these IO nodes to do
No. So the IO nodes are usually just for interfacing with the external IO. For the peer-to-peer streaming, I've typically seen it done with the FIFO.
I don't know. Specify it.
Yeah. Any other questions? If you have any other questions too, we're actually doing pretty good on time, so feel free to continue to shoot. All right, then it goes. Cool. All right. So on the FPGA so far, to recap, we've talked about the fact that you interface with the I/O using I/O nodes. We talked about float to fixed. I believe this is point 8, point 7. I think we talked about the differences in clocking. So a while loop will use basically it'll store the data in an intermediate register every single time, whereas a single cycle time loop will use one clock tick for everything in the loop. And then we talked about how you actually transfer data between the FPGA and the host. So either single point using read-write controls or with a FIFO. I believe those were 4 on the FPGA so far. And so now point number 10. What is point number 10 when you are moving from current LabVIEW experience to programming on real-time or on the RIO architecture? And so we've heard the term compile, or compile for, bit file. We're talking about an FPGA turnaround. And like I said, an FPGA at the end of the day is you are configuring the fabric on the FPGA. You're not actually running code on its operating system. And so what that means is your code is going to get eventually compiled to a bit file that the FPGA understands. And so sort of there's a process that goes through. All our compilers use Xylus compiler. So depending on the FPGA that your target has, it will use a certain set of compile chain tools. And then ultimately it'll compile it down to VHDL, and then it'll try and basically eventually try to map the system resources to the best of its ability. I'll get to your question in a sec. But that being said, so compilations can definitely be slow depending on how large your application is or how complex it can take anywhere from tens of minutes to hours really, depending on again the FPGA and the newness of the compiler tool, like the new Vivado compiler from Xilinx, they made it a lot faster than the previous ones. But then that being said, so our compilations are going to be the same speed as if you're using VHDL, but again, sort of different programming paradigm. And so your question? The question was, do you have access to actually the optimizations for the compiler in the background? I don't believe so. I think that's all just done by Xilinx. I don't know if there's. I also don't have really seen a specific use case for that. But again, I don't know, Mike, if you've ever seen the ability to actually change the optimization settings on the compilation at all.
There's some that are in the build spec for the FPGA.
Yeah.
But you don't have a lot of control over it.
Also with, and it's maybe a more advanced topic as compared to this session, but FPGA IP Builder, which is included in LabVIEW FPGA, allows you to do more tweaking on rolling of loops and other optimizations, but it is specific to IP blocks versus the full design.
Question?
Does the Xilinx compiler still not support Windows 8?
That's a good question.
I'm pretty sure Vivado does now.
IEC doesn't. I'm not sure about Vivado. I don't know. Yeah. So they don't have a definite answer on whether the new Vivado compiler supports Windows 8. I didn't think so, but he said I think so, so I'm not sure. Okay. Okay, you said yes. They have. If they said yes, then it'll all be yes.
Yeah, I have older cards.
The word is our word is talking to NAE that Vivado is supported. Yes.
Any comments on the Linux-based hard drives? Any changes?
Specifically this year or in general?
In general, any advantages to it?
Sure. Yeah. So the question was advantages of using a Linux. So right now, all of our newer targets, as of since, for example, like the Serio 9068, run a Linux operating system. There are different flavors of that. And a lot of our older targets ran a older version, like Farland, for example. I think the biggest advantage of moving to Linux is the fact that it's a lot easier to implement other Linux libraries. So it's a lot easier to import those in versus using our operating system. I think that's been the biggest optimization. This year, also specifically, the newer targets support secure Linux as well. So for people who've had security concerns. Those are the two biggest that I can think of for using Linux as well.
There's an entire session on that tomorrow.
Yeah, that's up. Yeah, tomorrow at 10:30. It's a real-time Linux stack down.
How many pins in that chip, the FPGA chip?
So the question was how many pins. It's gonna. I think it just depends on the FPGA. So different targets are going to have different FPGAs. I don't think I have the.
So it can be swapped to different chips?
Yeah. Yep.
Okay.
So for example, the SOM that I mentioned at the beginning of the session, I'm guessing, but I believe it has 128 pins that come off it that run directly from the FPGA. But yeah, it'll depend on the architecture.
But on the board it is fixed. How do you change it to different number of pins for the FPGA chip?
So yeah, that will be fixed, but usually that's not. I think that level of actual control is abstracted out for you because in terms of the HCL to actually interact with the I/O, that's all basically built into the I/O nodes. So that's usually not a kind of a consideration that you have to take. I don't know if that fully satisfies. I mean, so what is the use case that you're kind of thinking of?
I'm thinking, if my VI code is too big and I need to have a more powerful FPGA chip, so in that scenario, I may need a new chip.
So in terms of how that impacts the I/O, I don't think I've actually ever seen a use case where you can't interface with any more I/O due to the FPGA. Because your question is the difference between like resources, so that's sort of like slices and lookup tables and all that sort of type of stuff on the chip versus the actual pins. but I can also follow up here. Like, I mean, so was that kind of more general curiosity, or is it specific to your application?
Just some of the application testing because we don't know how big it is, and I don't know if the FPGA will be has that kind of capability.
In terms of the number, in terms of the channel count?
Yeah, the IoT. You know, suppose we need a lot of IoTs for a lot of sensors, input and output.
That's a good question. I don't know. Do you have any idea on that, Mike? Or is that you?
That's fine. I mean, usually it's going to come down to the hardware that you've got, and so you know, if you get C series I/O for compact Rio, you know, once you fill all the slots, that's going to be the maximum you can get. But we could chat afterwards about what your needs are, and you know, find what product would have the I/O count you might need.
The second option would be you could simulate the FPGA VI ahead of time to see what size of target you need before purchase as well. It's something to
Yeah. So for the research utilization, you can get estimates on that. Right. Yeah, question?
How much of the building process can you do without actually having physical FPGA?
So you can do really everything. That's kind of the next sort of part. You can basically do almost basically all of that except for actually interfacing with the I/O, obviously. So there's I don't think what's
simulating.
Yeah. So you basically you can still, so this is your VI on your FPGA. You can still use your normal debugging tools to have it actually run in simulation, even though you're not interfacing with the I/O. And basically have a pretty good validation of whether you think your result will present will work or not. Sorry? Yeah. Yep. So going back, so you have a couple options when you're actually building your compile. So if you have your VI, it's finished, you actually want to generate the bit file to run on your FPGA. So usually in your project, you'll have your FPGA, and then you'll have like a build spec like you've seen before for like an executable. And in this case, you'll create a new FPGA compile. There's a couple options in there, and then you can build it. Also, if you run the FPGA VI and you have it set to actually run the FPGA in on-simulated mode, then it'll actually kick off the compile as well. The three options that you have when doing a compile, the one that we really recommend the most in terms of sort of efficiency is running on our compile cloud. So we sort of have we take care of the uptake of the servers and making sure that you have enough resources on there for you. And so with, I believe you in 2015, if you have the standard service contract, the SSD, then you have free access to our compile cloud as well. So the caveat with that is we do not collect your block diagram or anything about the application. All we really collect is how often your compile is done and what time they're done, just to try and really optimize the service that we're able to provide. So with the cloud, you can also kick off up to 5 compiles simultaneously at the same time, because unfortunately the compiling isn't as deterministic as we were hoping it would be. So that way, if you kick off 5 at the same time, you would expect at least one to pass. The other option is you can get a compile farm license, and you can update your own or kind of maintain your own compilers in-house on your own network if you prefer. So you can have your own computers, and then you update and uptake and make sure that they're running properly. And then the final option is to actually compile on your local PC. So this involves installing basically a couple gigs of compile tools. So that is sort of one of the trade-offs. And whereas kind of when it's out in the cloud, it's often that's sort of always running. But a lot of people might not be connected to a network, and so in that case, that might be a use case for compiling locally. These are sort of like the three main options when you do compilation.
Where do you set the launch?
Sorry?
You said build it, give you a choice?
Yeah. Actually, let me show that to you. So if I went here, and I went to my build spec, and I build it. Sorry. I don't know if this will work. I'm not thinking it's a real one. Run on the FPGA target. I'm going to build. Yeah, so at this point, this is where you have your options. So you can either tell it run on local, connect to your network, so compile on your network, or it'll ask you to go to the, or you can go to the kind of the LabVIEW cloud. Yeah, that's what you choose. And you can also tell this is my default. Don't ask me again. This is the one I'm going to do. Good question. All right. And like I said, so you have all the different kind of debug tools available. So really, like I said, a compilation can take minutes to hours depending. So really, it behooves you to do as much simulation and as much verification of your design before you run the compile, because the last thing you want is, oh, like I should have put an and here instead of an or that's not the best example, but making sure you fully verify your design before you actually run a compile. One of the tools that we have to really help with that is this desktop execution node. So if you have your host VI, you basically can create a test bench where you specifically specify what your FPGA VI is, and then you give it either a file or an array or something like that of simulated data, and then you see, does it actually give me the output that I expected. So there's all these tools available that actually help make sure that you can properly run a compile. I would demo it, but I think I'm running out of time for this session. So I think that's the last part I have. So basically, 10 things that we talked about today. So you're moving from LabVIEW to a re-architecture. I would quiz you all, but it's been a long session. So the first, always use the project. The second is when you're programming on an embedded target, you're working with constrained resources. So again, within FPGA, you might have different, you only have a certain finite number of programming blocks. The third is you are programming on a real-time operating system, so if you want to give something high priority, you use a time loop versus a normal loop. The fourth is you have access to a watch clock timer, so making sure your system, if it were to crash or run out of memory, would reboot, for example. And the fifth, so if you have your embedded target and you're actually interacting with it over a network, typically that's how you're going to be debugging it through a network of PC, and you're going to have like a host executable running, and you're going to have your executable running without a front panel on your CPU. Then we talked about FPGAs and how you interface with I/O. So the sixth point was use an I/O node. The seventh point was float to fixed, and how you have to make those considerations and those trade-offs in terms of resources used on your FPGA. The eighth was the clocking, so single cycle time loops versus having the actual registers take up time. The ninth was how you interface between the FPGA and your processor, so either single point or you buffer it with a FIFO. And the 10th was you actually have to compile your FPGA code. So realize compilations take time. Always simulate as much as you can before you actually compile. And there's a couple of ways you can do a compile, either in the cloud, in your own network, or the so briefly before you guys go, some additional resources, because I just threw a fire hose of information at you. If I were to recommend, the number of times I recommended the CVO Developer's Guide to people, like, this has everything I talked about, but even more. It goes into all the details and all the whys. It's a fantastic guide, and it's actually formatted in a very kind of pleasant way to read. So I used to actually have this on my Kindle, and I was trying to read through the whole thing, but it's very in-depth, so it's very long. So, yes?
Is that generic enough for yours and fees?
So it is. That's a good question. So it's for USRP, I would recommend LabVIEW Communications. That's the product I work with a lot. But for it, so it'll have the how-to program on the FPGA still. The USRPs don't currently have like their own real-time operating system, so that part won't be relevant. But it would be at least relevant on like how to optimize my design for an FPGA, especially if you're using LabVIEW 2015. It doesn't talk about the RF stuff. High performance is going to be for like Flex Rio type of stuff and a lot of those type of applications as well. We also have a new course that we've come out with, so that we have a real-time and an FPGA course, and we've really kind of broken it down and rebuilt it into something more optimized in terms of like what is more important to you guys in the application areas and all that type of stuff. So it's embedded control and monitoring course. So this is something that is going to be helpful for you as you move forward with your project. Then I would highly recommend you can either follow up with me after the session or talk to your account representative or your field rep. Finally, in LabVIEW 2015, as before, there's a ton of examples to help you get started. So I think we've all had that like blank VI syndrome before. Don't start from the example. Start from the sample projects. There's the LabVIEW evaluation kit. So this is sort of for building your own embedded application and kind of really getting started on an actual hardware target. And so my colleague Deb who's in the back is sort of the one who typically runs these. But you can order these also online, and it's a really useful tool to kind of start to get your idea going. And then finally, these are the different sessions if you want to continue learning about compact Rio. So there's hands-ons. I think today there's one at 3:30 for motion and one today at 4:45 for vision. So you can interface these with motors and cameras. And there's a couple hands-on for just C-Rio, real-time, and FPGA tomorrow. And these are the upcoming sessions. There's a ton more, but today there's LabVIEW FPGA best practices, 10 differences between LabVIEW FPGA and LabVIEW for Windows. This actually goes way more into the details of FPGA programming as well. Choosing a software architecture, so architecting your code well is also always important. And then tomorrow, introduction to NIWeek real-time, and then there's a session after that on real-time operating systems for Linux Smackdown, and then there's more that come after that, but this is sort of to plan. I couldn't fit it all in one slide. There's a ton of stuff, so again, thanks for the questions, and if you have further questions, feel free to come ask. Yes?